Okay, now it's starting. Hey yo, what's up, YouTube? It's your boy JOSHABRAHAM. And we're back with the Biochemical Kinetics. No, it's still not showing up. What? YouTube, you're still not showing up. Okay, you should shoot up. You shoot up. Edit. Got it. This is a phase diagram question. Figure 1 shows. Where is figure 1? Oh no. How will I show this diagram? How can I show this to ChatGPT? Mm-hmm. So I do have the figure in my assignment sheet, and it's looking kind of weird. How can I give you the details so you can form the graph? Perfect, we can work with that. The easiest way is for you to give me the key details from the figure, like numbers, positions, shapes. That's the problem. I don't know how to say the shape. It's not a triangle. It's... Oh, come on, come on, come on, come on. So y-axis is T, x-axis to the left is selenium, and to the right is radium. The graph starts at the particular T and curves downward until it reaches a point which is also intersected by a line parallel to y-axis named T1, and from that point it started curving, it started to curve upwards and reach a point higher than the initial temp where the graph started. Did you get a picture? If you did, make me a Python script showing how the figure looks like. Let's see how well ChatGPT understands things. And I'm not even kidding. I can't wait to build my own AI. I just hate using someone else, some other corporate AI, even though they have much more data compared to if I start making one. But still, it feels good to have your own. Why did I say this? I don't know. I was just, I don't know, I was where did you come from? Where did you go? Where did you come from? Jaganano. You're back. Where did you come from? Where did you go? Where did you come from? Jaganano. What type of figure is this? Solid liquid phase diagram. Dot pi. Where did you come from? Where did you go? Where did you come from? Current. Oh brother. Oh brother. Nah, honey, I'm good. I could do whatever. Probably should not. I got somebody at home. If not leave mine, I'll leave alone. Nah, honey, I'm good. I could. Where is it? Where is it? So that's the XY axis. Where is T1? T1 is this? Oh, brother. Oh, brother. It's not how it is. No. Okay, a lot of mistakes. First off, there is only one line. As part, and it starts, it's a point then it goes down. In yours, it goes up. It goes down till it crosses the line T1. Then it goes up and stops at the level higher than the initial temp it started in y-axis. So if this is not working, I gotta change my weight. And I don't believe in ChatGPT when it comes to Python. I tried actually. That was kinda, that makes kinda sense. I could take this opportunity. Different types of slopes seen in graphs. Yeah. What's this one? Not this, bro. Think. T start at 120. Okay, let's say it starts at 120 and T end at 140. Okay, those two are correct. T minimum is 80. Uh-huh. You know what? Let me turn on uh stage manager. Yes. Okay. You somehow got the start, end, and now the curves are so the first slope downwards is kinda looking correct, but the upward slope after T minimum is almost like looks like a straight line, but the midpoint is kinda stop. It should work with just enter. Shift enter just now. Okay, you still haven't got it. So name all the columns in the graph. Like just number all the columns in the background. And I'll tell you the columns where the graph passes through. Now, can you write the program in a way so I can see the numbers in the graph? It's I don't think I think there's more than 10 columns. Come on. on, it's taking too much time. Hey Siri, set a timer for 30 minutes. Okay, that's a good start. Please, if I get this right, then that means please, please, please don't steer too much away from the right answer, please. Yeah, the curve is down. It should be upwards. How can I tell the change? $110 and the first descent should be passing through $110 and 0.2. But the line should be curved in a way that it passes through these points specific to the descent and ascent. Please. Specific points, because you're not making that slope, not slop. Slope. Gossip. How many more? Yes. I kinda did it. That kinda did it. Yeah. Yep. That's almost how the figure one looks like for the question. Gotta wash my hands. Oh, it's cold. Perfect. Now we have the face matching your figure. Okay, the T2 curve. Oh no. What? Why did you add the cooling curve? Come on. You. Oh, is it part of the question to have the cooling curve? Wait. Draw cooling curves in T. Oh shit. But wait. Think. Deadline 19th November. Oh, that's a lot of deadlines. Indicate the melting point of the pure substances. Indicate the liquids and solidus lines with different colors. Label all region faces percent. For labeling, mind the molar ratios of the selenium. So this is the cooling curve. I got it. Oh, come on. Stop confusing. So, okay, you did not need to do. Okay, so how do I do? Indicate the melting point of the pure substance. Here's how to approach it. Clearly identify the pure substance on the x-axis. Left end x equals 0 pure selenium. Right end x equals 1 pure radium. Okay. Look at the phase diagram at these points. Y-axis is the temperature. The melting point of the pure substance is where the phase line intersects the y-axis at its composition. For selenium, x equals 0, go vertically up to the phase line. Melting point of selenium. For radium, radium x equals 1, same idea, that y value equals. So this is the melting points. Mark them clearly, draw small dots or small horizontal lines on the y-axis at the intersectional point. So selenium. Exactly. Okay, so these are the melting points. No values are given, right? It's just now indicate the liquids and solidest lines with different colors. Wait. So radium Ra, yeah. That point usually is called oitic point in the binary alloy phase diagram. Solid liquid phase. Solid liquid is binary, yeah. The curve starts at melting point of it slopes downwards as the mixture melts at lower temperature. How does the mixture? Oh, mixture. Okay. That than either pure component. It reaches a minimum temperature somewhere in the middle. This is where the lowest temperature at which the mixture is still fully liquid. At this point, the curve slopes upwards towards the melting point of radium. It's often where a liquid mixture solidifies into two solid phases simultaneously. It's often where the liquid mixture solidifies two solid phases simultaneously in a simple oitic system. The x coordinates give the composition of the mixture at this minimum melting temperature. Okay. So from the x-axis, we could say that at this point, um, selenium is higher in composition compared to radium because the point is nearby selenium. I think I understand correct. It's x coordinate. Okay, the y coordinate. It's called eutectic temperature. So in your diagram, okay. So the eutectic point. So in the diagram, the eutectic point is nearby the pure Se compared to pure Ra. So the composition would be having higher selenium, higher selenium. So indicate the liquidus and solidus lines. That's the oitectic point. Now this part B, how Understand what these lines are. Liquidus line, the upper boundary of the curve. At this line, the alloy is completely liquid. Solidus line, the lower boundary of the curve. At below this point, the alloy is completely solid. Between these two lines, you have a two-phase region, solid plus liquid. In simple eutectic diagram for alloys that don't have a wide melting range, the curve you have may represent the liquidus line and the solidus line is slightly below it. Some diagrams only show one line. Wait. For alloys that don't have a wide range melting point, the curve you may represent liquidus line and the solidus line is slightly below it. Some diagrams, and you may have to identify them on the diagram. The curve starting from the melting point of selenium, dipping to T minimum, rising is usually the liquidus line. Solidus line would be below the liquidus line, roughly parallel to it, connecting the points where alloys. Okay, well, yeah, I do have a line. I think that's the solidus line. This is the liquidus line. Yes, I do have another line that's passing through the eutectic parallel to the x-axis, but that line joins the y-axis below the melting point of pure Se and Ra. That line is the eutectic line. Here's how liquidus line, the original curved line dipping, racing above the line is fully liquid. Okay. Solidus line, the line below the liquidus line, meets the eutectic line at the eutectic below. Eutectic line, the horizontal line passes. Okay, that's the eutectic line. It's not the solidus line. Lies below the liquidus line, meets the eutectic line at this eutectic point. Below solidus, it's fully solid. For a simple eutectic, the solidus line runs from. If you want, I can update your. No, I don't want to update. Label all the regions present for having in mind the molar ratios of selenium in the solid phase. Indicate two-phase regions. Indicate the eutectic line as well as the eutectic point. I know that one. Draw cooling curves. So I still haven't understood what is the solidus line. Okay, so I thought how do I find let me take a beep. I'm a monster. Exactly, you were close, but the solidus line is not eutectic line. Temperature above with which the alloy is fully liquid. So above this temperature, it's going to be liquid. Solidus line, temperature below which the alloy is fully solid. Between the liquidus and solidus line, this mixture is solid and liquid. Okay, so how do I find the solidus line? So the solidus line connects the points where solidification begins at each composition and meets the eutectic line. How to find for a SC-rich composition, move down vertically from the liquidus line until the mixture becomes fully solid. That temperature is the solidus point. Uh, what is the that's the melting point. Draw a curve connecting these points. From RE rich, same thing, move down. Oh, the solidus line usually mirrors the shape of the liquidus, but lies below it. Okay, it mirrors the liquidus and is it gonna be like this? It could be. So I'm guessing I connect the oitectic point. Oh, oitectic but above zero, connecting. So this is for copper and 30 minutes. God damn it! And that's the eutectic composition. That's the liquidus line. And it's a solid. So they basically started from zero. Huh? So the solidus points be below or above the eutectic line intersecting the t-axis. Who uses figure 2? Okay, so example 22 uses figure 2. Okay. Okay. I'm not gonna lie, the solidus line above the eutectic line. Again, from what I have understood, for the solidus line is the temp is that it starts at the temp where the pure substance stays solid. And here we are not given specific temperatures, temperatures. So it's safe to assume the solid temp is 0. For pure substance, the temperature at which it is fully solid is, what are you saying? For a pure substance, the temperature at which it's fully solid is its melting point. What? Example, pure SC melts at 120. It is solid below 120. Pure Ra melts at its solid below 140. So in the diagram, the left end of the solidus line starts just below the melting point, not 0 degrees Celsius. That's the solidus line? No, something's not making sense. Yeah, all these are starting from 0. What? Don't get it. Don't get it. Liquidus line, solidus line, solvus line. What is that? What the hell's that? Oh, oh, these guys meet at a point before, at a point in the eutectic line, but before it reaches the eutectic point. Oh, oh, what is the question? Indicate the liquidus and solidus line with different colors. How do I do that? Liquidus and solidus lines. Selenium and radium. Let's see if the radium, not radion. How do I calculate these numbers? Like there's an alpha value. Solidus, solidus, liquidus, eutectic, eutectic. You know what? I should check out YouTube.
I've been all around town, bass, stunning, drown as these sounds come in.
We're going to talk about the silicon germanium phase diagram. So this is what the phase diagram looks like. If you look at it, it has two axes. So the vertical axis, as you can see from here, is the temperature, and the horizontal axis is the composition of silicon in the system. So this is particularly in terms of the weight percent, which allows us to later to compute the fraction of each of the phases using the so-called level rule, and we're going to discuss in detail. Okay, so the phase diagram is a fundamental tool to measure any given region, phase, right? And then if you still look at that, right, you have
This is not the phase diagram.
your system, 1200 degrees. The liquid phase,
Do you have the specific one I'm looking for? Sub, yeah. Okay, I think that's, oh, whoa, 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 that's a big one. That's the one I believe.
Okay, so I think in the last few lectures we focused on this one is just a combination of these two. So now in the next, I think at most 2 lectures, probably I'll try to finish this lead composition in front of this region, in front of beta phase, so it can be stably converted into the solid. Okay, so that's the basic idea. So as you can see that, the growth of the eutectic transformation also involves a lot of local center of this alpha, and this alpha is what we call lambda. Okay, now this lambda is the same thing as if you were, let me see, to
I did not know they have
use a
lambda
notation.
in the diagram.
This is, we know that interface is going to be the source of the, and
What?
cause it whenever is,
Yeah.
okay, so put in A. So because when
What?
uh,
I don't
of
think
a
it's related to. It's just the graph kind of looked the same. No, this ain't it, bro. No. No. Bro, come on. They're not even trying, bro. No, no. Oh, insoluble phase diagrams. Muddiest point. The binary eutectic phase diagram. Yeah, I think that's.
Alright, we've talked about an isomorphous binary alloy. That's the simplest binary. Let's go to a slightly more complicated binary. That's the binary eutectic phase diagram. So we call this eutectic because it has a eutectic reaction. A eutectic reaction is one that has the following reaction as you cool down. It goes from a liquid and it splits into two different solids, which we'll just call alpha and beta, right? So at a solids. A and B can be single elements, but they could also be compounds, right? That could be, B could be Al2O3, for example, and A could be MgO, right? And you could look at, as you take MgO and you add Al2O3, you could look at the phase diagram that results, or it could be individual elements like lead and tin or bismuth and tin, okay? So, if this has a eutectic reaction, it will typically look something like this. Now, the exact position of all these points, the lines and the intersections, are all, of course, tunable to the exact system that we're considering, but they typically look something like this. Now, we need to label these phases. At high temperatures, we're going to have our liquid region up here. Now, just like before with the isomorphous binary, right, where we had this region of liquid and then we had solid and the region in between them had both, we have the same thing over here. We've got a liquid region, and then we have, let's say, a solid region, alpha over here, and a solid region, beta over here. And that gives us regions like this, liquid plus alpha, and liquid plus beta. And then in the middle, we have this region where you have alpha plus beta. Okay? So can you spot the eutectic? The eutectic point on this diagram where you have this reaction taking place, liquid turning into alpha and beta, as you cool down. Hopefully you can see that it's right here at that point. At that point, as you cool down, through that point, if you're at exactly that composition, and we call that composition CE for eutectic usually, you would go from a liquid at the CE composition to two solids. Your solid would have this composition over here, if it's alpha, and the beta would have that composition over there. So this would be the composition of the alpha phase that forms, and this would be the composition of the beta phase that forms. Okay? So this is a binary eutectic phase diagram. And just like we could do the Gibbs phase rule before, we can apply the Gibbs phase rule here, right? For example, how many degrees of freedom are present at the eutectic point? So at this eutectic point here in the middle, we could apply Gibbs phase rule. So we would say, give ourselves some room, we know that P plus F equals C plus N. So how many phases are present right at that eutectic point? Well, we've got liquid in equilibrium with alpha and beta, so 3 different phases. So 3 plus F equals C is the number of components in the system. So how many components do we have? Well, it's going between A and B, so we have 2 components. Plus N, where N is the number of non-compositional variables. And in this system, the only non-compositional variable is temperature over here, so just 1. You could have also made this plot, instead of against temperature, you could make it against pressure. But if you want temperature and pressure, it would have to become a 3-dimensional figure, which is hard for us to sort of look at and interpret. So they usually show these as 2-dimensional figures. In any case, you can see that for this case, at the eutectic point...
So, for in my case, if I understand the... Okay, it should be something like this. Huh? Yeah. And between that point, the solid selenium exists and solid radium exists. And here, both solid selenium and radium exist. Yeah, something like that. And here it's only liquid. And wait. And here it's here it's basically liquid selenium and solid radium. Huh? Yeah, something like that. L plus beta. Okay, the liquid form. Okay. Liquid mixture of selenium.
F equals 0. In other words, there is only that one point on the
What
plot,
the f is this?
right there, where you can
Stop!
have all 3 of those phases in equilibrium.
Ads, bro.
Now, you
the
might
fucking
ask,
ads.
well, what about right here? What about on that point? Fair enough. You also have liquid plus beta and then alpha plus beta, so you have 3 phases in equilibrium, but the fraction of those phases has changed, and we're going to learn about that in a few videos.
Do we have fraction type of quest? Indicate the 2-phase regions. 2-phase regions would be... Wait. Label all regions, mind the molar ratio of selenium. Label all regions / phases %. Okay, it's already 30 minutes. Ah, damn it. Let me heat up my hands. Push up. Push ups time. Push. Hey Siri, set a timer for 30 minutes. I have to do one thing, and I could set a timer. Hey Siri, set a timer for 5 minutes. I'm gonna mute the mic, and I'll be unmuting in 5 minutes. Yep, I apologize for wasting some time. I was doing extra project. So where were we? Where were we? Mm, solid phase liquid diagram. I got a chat. Got it. You guys gotta hear this. Where is it? So Jesus died to pay the price for our sins and rose again, offering eternal life to those who believed in him. We got a we got a Christian out here. Let me see this account. Is it the follower of Jesus? I don't know what I am. Okay. It's just a freaky account, I guess. Well, I appreciate the comment, even though it's a bit towards the religious side. It's okay. Dude, why is it cold? It's pretty cold. What the? So what were we doing? Yep, the binary eutectic eutectic phase diagram. It starts eutectic line with This is a simplified diagram. This is perfectly safe for your assignment when exact temperature aren't specified. Okay. So I believe I could use this. Where is it? I believe I could yeah, use exactly this one. Alpha plus liquid. So here what would the alpha be? It would be selenium and beta be radium, and here it would be solid selenium plus liquid rubidium, both to be solid. These are also solids, right? Yeah, from what I understand. Solvus. Okay. Solvus appears in some phase diagrams is different from liquids and solids. Here's a clear explanation of what the solvus is. The solvus line shows the limits of solubility. Mm-hmm. How long have I been streaming? I'm sorry. It should be 1 hour, right? It's about 1 hour 40 minutes. God damn it. It's a solid solubility. The mixture separates a solid phase, a single solid phase. Okay. So here the solvus. Actually, I think this looks pretty easy, bro. 30 minutes? Gah. Yeah, I'll end the stream here for biochemical kinetics. I kind of understood what it should be. I will now continue with sequence analysis. Then I'll continue with this again. I'll make sure I complete the first question. I gotta make sure I do that. Well, peace out, YouTube.